Our next speaker is Dr. Victoria Hamilton. She's the chair of the MEPAG, the Mars Exploration Program Analysis Group. Welcome to the conference, Dr. Hamilton.
Thank you very much. Thank you for having me. I'm very sorry that I can't be there with everybody in person today. Unfortunately, I had a pre-existing travel commitment earlier this week and just got back last night. But I really am excited to talk to you about the future of Mars exploration. I'm hoping that Abby just gave you some really great eye candy and talked a lot about the science of Mars. What I want to talk about today is the future of Mars exploration. And so I will go over very briefly the fleet of robotic missions at Mars that are currently underway and have been going on, some of the ones that are no longer active, and how they fit into an overall program of Mars exploration. I want to spend a little bit of time talking about the development of priorities, because how we develop our priorities is something that I think a lot of people maybe don't have very much insight into, and yet I think it's a really important part of understanding both where we've been and where we're going. And so from that, I will lead into talking about NASA's current Mars future plan, what the next decade or two of Mars exploration looks like. And then I'll transition over to applications of nuclear technology to Mars exploration, based on a singular event that I attended, but an example of how Mars science is starting to be integrated into those kinds of conversations. I will give you a disgracefully short one-slide overview of the Moon to Mars program. That program, understandably, has been largely focused on Artemis and lunar science right now. But we're moving into the early stages of additional Mars expansion in that. And so we'll talk a little bit about where you can find more information about that. And then finally, I'll conclude with the budgetary outlook for Mars exploration going forward. But I wanted to start out with an overall sort of thought about Mars exploration, which is that the evolution of our robotic capability has really dramatically changed the human understanding of Mars as a planet, but Mars as a planet within a solar system, and the impact that the data we get from Mars has on our broader understanding, especially because it can give us information about periods of time that are no longer really accessible to us on Earth in an unaltered kind of state. So the next phases of that will be sample return and human exploration, and they will undoubtedly be step functions in our understanding. So here's a fleet chart of NASA missions and some of our international colleagues' missions to Mars in the last 20 some odd years. And what you'll see is that there's a whole suite of landed missions, rover missions, orbital missions that all complement each other. And Mars exploration as a program has been so successful because it takes what we learn from early missions and takes that and adapts it and builds upon it and complements it with the subsequent missions. And so you can see kind of what we've been doing in the last 20 some odd years and where we hope to be going in the immediate future. But I think what I'm talking about here is really well graphically represented in part by the arrows at the bottom of the figure. So back in the very late 90s, early 2000s, we learned that there was in fact water on Mars, in Mars, beyond its presence at the polar caps. And so that led us to many missions and instruments and investigations focusing on where that water is. And that, of course, leads us into the idea of habitability and where are habitable locations on the planet Mars. And then that, of course, brings you to the question of, well, who was maybe habiting it? Is there evidence of fossil life on Mars? And now coming into the next several years and decades, probably, of exploration, we'll be looking for actual signs of extant life, not just fossil life. And of course, interwoven throughout all of that is how Mars exploration feeds forward into the preparation for human exploration. So let me spend a little while talking about the development of priorities for Mars exploration. NASA, of course, has its own internal processes, and that's something that you should hear about from someone at NASA. What I'd like to talk about are some of the non-NASA sources of information, and I'll focus on two of those today. The first one is the Mars Exploration Program Analysis Group, MEPAG, of which I am currently the chair. This is a volunteer organization that supports the Mars Exploration Program in a variety of ways. We host meetings. We're a volunteer organization of members of the community, scientists, engineers, and other interested people. We're open to anyone in the world who wants to participate. We will provide input to NASA via topical reports. We also maintain a document called the Goals Document. This is a living document that outlines the objectives or the goals and objectives and investigations that the science community believes are the top priorities for Mars exploration in the robotic program going forward. We'll talk about the fact that human exploration in that document is also increasingly integrated into that science, both the science that is enabled by human explorers, as well as the science that can be conducted and conducted better in many cases by human explorers. Something important to understand about MEPAG is that we are generally not tasked with specifically taking into consideration detailed budget profiles when we do our work, and we are not an advisory committee. The other large source of information from the outside going into NASA on Mars exploration is the national academies. And they have two different primary mechanisms for producing that information. The first are ad hoc committees that are requested by NASA, and they usually have a very specific statement of task, questions that NASA would like to have answers to. Oftentimes that can include summaries of the state of the field or the technology or whatever it may be. And so those reports can cover science topics, they can cover technology, they can cover things like programmatic issues or policy. Those committees are generally comprised of members of the community, science and engineering communities, others as appropriate, including members of the national academies. The other major source of input to our priorities are what are called the decadal surveys. And the decadal surveys are performed for each of the major divisions within the Science Mission Directorate of NASA. So planetary science is the one of relevance to Mars, but there's also decadal surveys for things like earth science, astrophysics, heliophysics, biological and physical sciences, and so on. These decadal surveys are conducted by congressional mandate, and NASA sends the requests to the academies to conduct these studies. They too are primarily comprised of scientists and engineers and other subject matter experts on various topics relevant to the robotic exploration of our solar system. This group, in fact, is tasked with undertaking detailed consideration of likely future budgets and making sure that different missions and different activities are phased through time in such a way that they can be conducted within the budgets that are anticipated. And then the other thing these documents do of fundamental importance for NASA is make actual recommendations about scientific priorities and flight mission priorities. And because these reports are congressionally mandated, Congress expects NASA to follow these decadal surveys to the best of their ability and execute them as designed. So in the latest decadal survey, which was released in 2023, the highest scientific priority for the robotic exploration in planetary science was Mars sample return. And this is not the first time that this has been the top priority of a decadal survey. It was the top priority of the previous decadal survey, and it was the top priority for Mars in the decadal survey prior to that. So this is a long-standing community priority to get samples back from Mars. And this prioritization really does reflect how important we believe these samples will be to enhancing our understanding of Mars and as an object within our solar system. Beyond that, it also will provide substantial information for planning for human spaceflight missions and human explorers, not just in terms of the science that they might do as follow-on science, but also to help development of things like spaceflight systems, everything from HABs and landing systems to, understanding the dust, not just as a particulate that will get into everything, but its chemical reactivity and, issues of health and human safety that will be informed by understanding what is really there on the surface in a way that we can't from robotic missions. The Decadal Committee, beyond that, also fully supported the continuation of the Mars exploration program as a program, precisely because it does allow for a very strategic approach to Mars exploration. The other mission that was prioritized for Mars was a concept called Mars Life Explorer, which was an extant life detection mission. This would be a medium class Mars mission, which in the decadal definition is a mission on the order of $1 billion, $1.5 billion or more, whereas flagship missions such as Mars sample return are usually in the several billions of dollars and up. So I wanted to talk a little bit about technology priorities identified in the Decadal Survey. The technology chapter of the Decadal talks both about short-term and very long-term advances that we should be looking towards in furthering our exploration of Mars. And that longer term time frame goes as much as 20 to 40 years beyond the term of the decadal itself. And it includes a wide variety of topics. It's not very restrictive in that sense, but most of the technology developments in one way or another are aimed at reducing mass, power, volume needs for instruments and flight systems. That not only helps keep cost in check, but it also helps us with development time. And as a result of all of that, making sure that we can be as productive as we can possibly be when we do get there and perform at our best capability. And that involves maturing a lot of technologies to be ready to fly on a spaceflight system. In terms of the priorities the Decadal identified, they were focused very much, of course, on general scientific instrumentation, in particular, those aimed at life detection, especially with that mission priority in mind. But there are a lot of other technologies that could benefit from technological development, such as more complicated sample handling than we can currently conduct, the ability to operate in extreme environments, both hot and cold, understanding and developing better communication systems that allow us to transmit more data and do more science as a result. All kinds of issues around mobility, whether that's entry, descent, and landing, or mobility once you're at Mars. Issues, of course, around planetary protection, RTGs, power systems, and subsurface access. They also identified disruptive technologies that these would provide, again, step functions in our capabilities now, not just in our knowledge. And so those are things like increasing use of commercial launch systems, quantum computing and AI and machine learning. We'll talk in a moment a little bit about the nuclear thermal propulsion and electric propulsion that could really change how we get to places and how quickly we can do that. Commercial exploration as an endeavor where NASA is not the only one flying things to other destinations to do science. So an example of that is the commercial lunar payload services and the potential for something like that to be started at Mars in the near future. And of course, in situ resource utilization has long been an area of technological interest and continues to be and will be for the foreseeable future. So with all of that external input in mind, plus NASA's own strategy documents, they have developed what we colloquially refer to as the Mars Future Plan. And that document covers the period from 2024 to 2044. And it was released in December of last year. It covers 3 specific science themes. First of all, exploring the potential for Martian life, supporting the human exploration of Mars as that becomes closer to becoming a reality, and then also revealing Mars as a dynamic planetary system. The document also recognizes that we're in an inflection point with this program. Mars Sample Return is a costly flagship mission, and most of the budget in the last few years, and as anticipated to be in the next few years, heavily skewed towards getting MSR finished. And so within that time, it does mean that there's slightly less money to do Mars exploration as we have been seeing it for the last couple of decades. This future plan, therefore, focuses on the conduct of smaller, more targeted missions that are able to be flown at a greater rate than some of the bigger missions we might be accustomed to. I'll note that that document does not really talk too much about advanced nuclear capabilities, but in large part that is because those kinds of development efforts are not under the purview of the Mars exploration program per se. They're actually held in other parts of NASA, other directorates within NASA that are focused on technology development across NASA. The graphic here on the right is part of the future plan published by NASA. And on the left, it asks the very simple question, where do we want to be in 20 years? What do we want to be able to do? We want to be able to get to compelling places, do systematic studies of Mars the way we are able to do them here at Earth, and make sure that we can get back as much data as possible to maximize the scientific return of our missions. And so the right-hand side of that chart talks about how we enable that. How do we get there? And so that is through things like more affordable opportunities for flight missions, making sure we have the appropriate infrastructure to do all of the Mars missions that we want to do, make sure we're doing the right targeted technology development, and make sure that we have a diverse community of people, scientists, engineers, and others who are all having a say in how we go forward. This is another graphic from the future plan, and this helps to contextualize again how this is approached as a strategic endeavor. So on the left, you see some of the outcomes that have been achieved from the last couple of decades of Mars exploration. And so that's things like following the water, getting into habitability, looking for life, getting ready for humans, things I've already talked about a bit. And then towards the right, you see how we anticipate being able to build on those things in the next couple of decades, where we're able to access materials such as ice that have not been something that we've been able to do just yet. Making sure that we're able to continue to access a broader array of surface and subsurface environments, making sure that we're leading the way in science for human exploration, getting to places that have been hard to get to historically, and then expanding our ability to return more and more diverse materials. So now I'm going to shift over to talk a little bit about nuclear technology at Mars. This is not my area of expertise by any means, but what I wanted to talk about was a very specific workshop that I was invited as MEPAG chair to attend in December of 2023, and that is the Accelerating Space Science with Nuclear Technology workshop. This workshop resulted in a report, the cover of which you see there at the right, and it is issued by the Institute for Space Science and Development, and you can go to their website to download this report and see what it says. There were sort of twofold complementary goals. The first of those was to invite together technologists and the science and planetary science and engineering community and get those groups talking to each other and understanding each other's needs. So the first part of that was making sure that those of us in the science community across the solar system, not just at Mars, understand what advances are being made in nuclear technologies, both for propulsion and for power generation, so that we could think about how those things might be used for deep space exploration. And then conversely, knowing all of that, we got into breakout sessions and talked a lot about how we perceive those technologies benefiting deep space science. And so how we would use them to really, again, enhance and grow our ability to do deep space science at NASA. There were 5 major topical outcomes of the workshop, not all of which are directly important to Mars exploration. A lot of them relate to things like being able to improve capability and access to outer solar system destinations. Examples of that are, being able to minimize the number of gravity assists because you have the power to get to where you need. And that means you get there faster, and then you can do more science when you're there. Nuclear propulsion has the ability to also increase launch period flexibility. Planetary launch periods are one of the biggest constraints on our ability to fly all the missions we want to fly, because you can't always launch whenever. You have to, you're at the whims of physics, and they're not really whims, they're just irrefutable laws, and you've got to work around them. And so being able to expand our launch periods gives us a lot more flexibility. And an example of that is in the decadal survey, for example. I think the outer solar system folks would really, really have liked to had a prioritized a mission to Neptune. But unfortunately, the launch periods are very, very restrictive for the foreseeable future. And it was simply determined that that was just not a feasible mission to prioritize at this point in time. And so, in its stead, the Uranus Orbiter and Probe mission was prioritized. It's a wonderful mission. It will return wonderful science, but it's a little more accessible in the time frame that we were talking about with the decadal survey. The other advantages come with being able to have the power to launch bigger, more massive systems. With more mass, you can include things like more radiation shielding, and that is important to being able to deliver the science payloads and have them keep working as long as possible. Increased power can also be used to increase communication rates. To be able to transmit more data faster enables us to do that much more science. It also enables us to operate instruments that require more power. Power is a huge constraint on spaceflight systems, both operating spacecraft and operating instruments. And so again, I've touched on this in other ways, but getting more capable vehicles to distant locations is always going to be a benefit and help us do the science we really want to do. Now, there is a caveat that goes along with all of this that we recognized as part of this workshop, which is that in order to take advantage of these technologies, within the current framework of NASA budget realities, we concluded that these systems cannot be so expensive that they dramatically change the cost profiles of our missions, making them much larger and more costly. These systems need to either be very affordable or they need to be provided in a partially subsidized manner so that the mission costs don't dramatically increase. Where for example, $800 million orbiter to Mars, may get a power system or propulsion system that would make it far more capable. But if it makes it a $2 billion mission, then that's no longer feasible. So we all agreed that in order to achieve this, the development of these systems really needs to look for the commonalities between mission applications, not just deep space, but all markets. That includes things here on Earth, and then make sure that we're designing in such a way that we can realize economies of scale and keep costs down, especially for the deep space applications. Okay, and here is my one woefully inadequate descriptor of human exploration of Mars. Really, this is to touch on a topic that I know is important to this audience. But Moon to Mars, as I said, the vast majority of it has been focused on lunar exploration right now, the Artemis program, getting that off the ground and successful. But fundamentally, this is a long-term plan for exploration that includes sending humans to Mars. And I think it's really important to understand that NASA has defined this program as having three pillars that are all equally important. And science is one of those. And that's really wonderful to hear. National posture and inspiration are also incredibly important aspects of why we're undertaking this activity. The document that you may or may not be aware about is the architecture definition document. This is the primary publicly available document that outlines things like the objectives, the needs, the capabilities that systems are going to have and need to have, not just to get to the moon, but also to get to Mars. And what it does is it outlines and guides decision making, and it identifies important factors that flow down from one decision to the next. And it helps identify the decisions that need to be made first because they have so many knock-on effects. One of the things I'll point out, this architecture definition document is well over 400 pages. There are white papers, there are ancillary materials. There's a tremendous amount of information here that I couldn't do justice to, even if this whole talk were about the subject. But on the right is an example of priority decisions that need to be made for Mars human explorers. And so on the left of the dotted line in this diagram are decisions that were identified in the 2023 version of the architecture review. And so you can see that they relate to kinds of different topics. Mars science priorities is right there in the middle because what science we want to do is going to dictate a lot about the number of people we need, the power systems we need, what we're going to, what cadence we're going to do all of this on. On the right-hand side, you see decisions related to other aspects of such missions like planetary protection, how long we can have people there, and so on. And so these were added in the 2024 version. And so we expect to see more coming in. This is an annual process, the updating of these documents. And so the details for Mars are starting to get fleshed out more and more. And I expect that we'll see more details about Mars in the coming revision in the first quarter of next year. Integration of all of this with the actual science community of Mars scientists has been a little hit and miss sometimes, but I think we're making a lot of progress there. Part of that is due to the fact that the science community resides in a part of NASA that is purely devoted to science, the Science Mission Directorate, whereas the Moon to Mars program is part of the, Exploration Systems Development Directorate. And so getting communication across those borders takes a little bit of effort, but I think we're getting there. Okay, so I'll start to wrap things up by talking about the budgetary outlook. I think I'd be lying if I didn't say that we're facing a very uncertain future right now. The Science Mission Directorate at NASA, which is responsible for all deep space exploration and particularly of relevance here, the Planetary Science Division, really hasn't experienced the continued investment in deep space exploration that the decadal surveys, not just the planetary one, but all of them have anticipated. A lot of that is due to the fact that we find ourselves in a recurring situation of continuing resolutions and delayed budgets from Congress. And that typically ends up resulting in flat budgets. And then once you account for inflation, those flat budgets are really cuts. And so we're really not making forward progress. We're sort of treading water at best. And an example of that is the review and re-architecting of Mars sample return that has somewhat stalled because of our inability to get commitments on budgets. Also factoring in here is that the president's fiscal year 26 budget request, or what I'll call the PBR, would cut NASA science overall by nearly 50%. It is aimed at canceling more than 24 missions across NASA science. And specifically with respect to Mars, it would cancel Mars sample return, as well as two ongoing missions, Mars Odyssey and Maven. And I think that that latter cut is especially painful because these are missions that have been tremendously successful. They're still returning great data, and they are pennies on the dollar for what it would cost to fly new missions. And so the idea that we would turn them off before they're absolutely incapable of doing anything else is something that I think is deeply unfortunate. Now, when we look at the appropriations process in Congress, the House and the Senate have gone through their initial appropriations markups of the president's budget request, and they would largely reverse these cuts in planetary science in particular. But until we have a fiscal 26 budget, NASA is generally expected to plan to the president's budget request. So that's led to a really high degree of uncertainty in the last several months about what would be happening in now that we're in the new fiscal year, what to expect. And that's caused a lot of concern. Certainly, the government shutdown that we're all experiencing right now, and then the continuing resolution that is expected to come out of that, only add to that uncertainty. And then another factor is the fact that OMB has dictated that they may not spend the money as enacted by Congress. That said, my last slide, I don't want to end on a down note. There are positive signs. It's been reported that immediately prior to the shutdown, the acting administrator, Sean Duffy, directed NASA headquarters to plan to the lower of the congressional markups, and that's the House markup. And that actually includes $300 million for MSR. Overall, there's strong support for Mars exploration and planetary exploration in general in Congress and in the public. I think it's a major driver of science and technology in this country and is really a source of leadership in the world. And, I think we can't discount the strength that comes from the fact that the exploration of Mars in particular is something that is tremendously inspirational, especially as we look towards Mars sample return and human exploration. Thank you very much. Be happy to answer any questions you have.
Thank you.